we'll start with a research paper session. We have 7 contributions for you that have been sent in to us, to LINHAC, and an international program committee has been looking at these, evaluating these, and they were under the leadership of our co-chair, Niklas, here. So Niklas, I'm giving over the word to you.
Thank you, Patrick. So, to today's program. So, as Patrick said, we're now going to go over to the research part. So, I was asked to be program chair for a selection committee. So, for those not familiar with the process of research papers, etc., typically researchers write research articles, looks something like this, and that then some number of pages where they present their ideas, their methods, and the results. They submit them to committee, and the committee then discuss these papers, and select some set of these papers. We got several really good submissions from countries like the USA, Canada, Sweden, and Switzerland. And from all of these papers, we selected 7 papers that are now going to be presented. In this session, we're going to have 2 of these research papers, and then we're going to take a break, and then 5 more papers. Now, to give the presenter some time, let's get right into the program. So, just going to be very high-tech and find who the first presenter is. So the first presenter is Kanav Vats. He's a PhD student at University of Waterloo. He is supervised by Professor David Clausi. His research interest is in computer vision, machine learning, and hockey analytics. So please take it away.
Hi everyone, this is Kanav Vats from the University of Waterloo. And in this video, I'm going to present our work evaluating deep tracking models for player tracking in broadcast ice hockey video. So the motivation behind this work is that although commercial solutions for hockey player tracking do exist, to the best of our knowledge, no data, networks, or performance metrics are made available. And prior research on hockey player tracking uses handcrafted features for tracking, and there is no published research for hockey player tracking that uses the recent deep learning based tracking methods. So as far as the challenges are concerned, there are a lot of minor occlusions and board occlusions in an NHL broadcast video. The camera keeps on panning and zooming, which also poses a big challenge. Plus sometimes there are big occlusions and clutter on the scene which pose a challenge to tracking algorithms. Now, in order to conduct this study, since there are no publicly available hockey datasets, we had to create our own dataset. So we created a new dataset in which there are 84 broadcast NHL clips at 30 frames per second with 720p resolution, extracted from 25 NHL games. The dataset is split such that 58 clips are used for training and 13 each for validation and testing. Also, the split made is game-wise so that there is no inherent bias that remains in the dataset. Now I shall discuss some statistics of the dataset that we created. In this plot, you see a bar chart where the duration of each video is shown. As you can see, the longest videos that we have in this dataset are somewhere between 50 to 60 seconds, and the average duration of a video in this dataset is basically 36 seconds. The current slide compares our dataset with other popular tracking datasets used in the literature. We compare it with the MOT16 and MOT20 datasets, which are pedestrian datasets, and KITI dataset, which is an autonomous driving dataset. As far as the number of sequences and frames are concerned, our dataset is actually bigger than these datasets. Although one important thing to notice is that the bounding box density, or the bounding box divided by the number of frames, is actually less in our dataset because there are generally limited number of hockey players present on the ice rink in a broadcast camera field of view, and there are generally a lot of pedestrians present in these pedestrian datasets. In order to annotate the dataset, we used an open source annotation tool called the Computer Vision Annotation Tool, which is illustrated in this slide. Now, this tool gives us the freedom to draw bounding boxes over each player and give them their team and identity label. Also, there is an interesting interpolation feature which uses the motion between successive frames to basically propagate the bounding box labels, which makes it easier for the person to annotate the dataset. So as far as the annotation process is concerned, 15 annotators annotated the whole dataset. Also, the average time taken to annotate 1 minute of video is 10.45 minutes, and to annotate all 84 videos it took 527 minutes. The same ground truth identity is assigned to a player leaving camera field of view and re-entering. This is different from the pedestrian datasets. Also, when players were occluded by other players, revision of annotations was performed to ensure high quality. Now I shall talk about the methodology. In this work, we tested 5 state-of-the-art algorithms that were tested on the hockey dataset that we created. The 5 state-of-the-art algorithms that we used, 3 of them used the tracking by detection paradigm. In this paradigm, there are 3 steps: the detection of players on the screen using an appropriate object detector. Then we calculate affinity or appropriate features from these detections so that they can be matched with the existing tracks. And then finally, we use an inference algorithm to come up with the final result. 2 of the tracking algorithms that we use the joint detection and tracking (JDT) framework. These algorithms either convert an object detector to a tracker or perform detection and re-ID or affinity computation using the same network. The table below gives a short summary of the trackers that we test with our hockey dataset. First, we test 2 tracking by detection networks, sort and deep sort. Both of these networks use a common filter, but one of them uses simple intersection over union based re-identification, and the deep sort networks uses deep neural network features for re-identification. Then we test 2 JDT algorithms with different flavors. The tractor algorithm uses separate detection and re-ID networks, but the Fairmont network combines detection and re-identification. Finally, we test an offline tracking by detection framework, which is MOT Neural Solver. This network performs tracking by converting the whole scene into a graph. Players are treated as nodes and they are connected with edges. And then it does graph message passing and classifies the edges to determine whether 2 players belong to the same track or not. So for the tracking by detection algorithms, sort, deep sort, and MOT Neural Solver, player detection is done as a separate step. So for this, we fine-tune a faster RCNN detector on the hockey dataset, and we obtain an average precision of 70.2 on the test set. So this is a very good detection performance, and in comparison, when this model gets tested on a famous computer vision dataset called MS COCO, it only gets an average precision of 40.2. This video shows the detection results, and as you can see, apart from some major occlusions between players, the results of the detection network are pretty good, as you can see these consistent bounding boxes over the players present on the ice rink. So before coming on to the results, I would first like to discuss the accuracy metrics that we have used for tracking. We use 2 accuracy metrics, the multi-object tracking accuracy MOTA and the identification F1 score IDF1. Another metric is the number of identity switches, which is basically if a ground truth identity I is being tracked with an ID J, but the last assigned ID was K, which is basically not J. So I would like to explain these metrics with the help of this figure and which metric is good or bad. So consider this figure which has 2 subparts, small a and small b. In both these parts, the ground truth identity is capital A, denoted by this black line in both these figures, and the tracked identities are these colored lines 1 and 2. In part A, as you can see, first of all, this ground truth identity A gets tracked by this predicted identity 1. After that, there is an identity switch and it gets tracked by this ID 2. In part small b, there are 2 identity switches. So first of all, this capital A identity gets tracked by this identity 1. After that there is an ID switch, and again there is another ID switch, after which the identity changes back to 1. So as far as MOTA is concerned, MOTA penalizes this figure more as compared to this figure because there are two identity switches. But if you look closely, as far as sports tracking is concerned, we prefer small b part more because in this part, the capital A ground truth identity is being tracked more consistently by a predicted identity, that is 1, right? Because in more than 50% of the length of this ground truth identity, it was being tracked by the identity 1, but in part small a, it was only being tracked for 50% of the time. So the IDF1 metric prefers this case over the case A. So this thing is more favorable for sports tracking, and hence we prefer IDF1 metric more as compared to the MOTA metric. So the table below shows the performance of the tracking algorithms. As you can see from this table, the first thing to notice is that the multi-object tracking accuracy, MOTA, is pretty high for all these algorithms used, above 90%. This is because the MOTA metric favors the performance of the detector in calculating the metric. As you can see, this is the formula of MOTA, and it involves the false positives, false negatives of the detector and the identity switches divided by the ground truth. Now the thing is, since the performance of the detector is very good in hockey, because there are limited number of hockey players on the ice rink and the players are mostly visible throughout the game, due to which the performance of detector is high, and as a result the MOTA of these algorithms is also pretty high. Now we shall come on to the IDF1 score. Now as far as sort and deep sort is concerned, the IDF1 score of deep sort is higher than sort. This is because the deep sort algorithm uses deep neural network based re-identification features, and as a result we conclude that these deep features perform better in hockey tracking as compared to simple intersection over union features used in sort. Now this is the performance of the JDT algorithms, and among JDT algorithms the fair MOT performs the best, evident by the highest IDF1 score. But the best performance is shown by the MOT neural solver model, which is basically an offline algorithm which uses graph message passing for tracking. Now the highest performance of MOT neural solver is evident by the high IDF1 score and low identity switches. And the reason why MOT neural solver performs so good is because it does not use any motion model assumption and simply treats tracking as graph classification. Now the table in this slide shows the individual performance of the 13 test videos. Now as you can see, there are videos with very high IDF1 score, 78, and there are videos with low IDF1 score, 49. And we shall analyze and investigate this video number 9, whose IDF1 score is not very high, which has 30 identity switches. We shall see what the main cause of error in this video is. So this video shows the results for video number 9. These numbers over each bounding box shows the predicted identity of the tracker. Now as you can see, upon minor occlusions the identities are still maintained, but still the IDF1 score is a little low, 53. That is because whenever these players get outside the camera field of view and re-enter once again, they are assigned a new identity, and that is because it is very difficult for the tracker to give consistent identity to a player when he goes outside the field of view and later comes in after some time, because there are no reliable features available to the tracker to re-identify the player under such situations. Now as we saw, the main culprit in tracking are pan-identity switches, which are arising because of a player going outside the camera field of view and coming in once again. We shall try to estimate the number of these pan-identity switches so that we can see how much they are contributing to the error. So let's say you have a video where the ground truth identities are 1, 2, 3, and 4. Now let's say the ground truth identity 2 is present in frames 1 to 6. Then there is a gap. After that, the ground truth identity 6 again reappears in frame 49. Now, since we have very good quality detections, this is only going to occur if the ground truth identity 2 was out of the field of view at frame 6 and came back in after frame 49. For example, in video number 9 for the ground truth identity 11, we see that the ground truth identity, there is a big gap between frame number 574 and 670, and we see later on in the video's demo this was actually a pan identity switch. Now in this video we see an example of how the pan identity switches are calculated. Now notice this ground truth identity 11, which is present in frame number 561. Now when we see, he goes outside the camera field of view and re-enters once again. Now right now, since this is ground truth data, he still has the identity 11, but in the predicted tracks, it gets registered as an identity switch. Now in this video where tracking is done, we see that the predicted ID of the ground truth ID 11 is 18, and as we see as this video goes on, this ID 18 gets changed to ID number 36. So from the previous slides, we saw that whenever there is a big gap in the ground truth identity frame numbers, it gets registered as an identity switch when it comes to the predicted tracks. So that gap has to be sufficiently large to estimate the number of pan identity switches, and upon minor occlusion, we found an appropriate value to be 40. Now we plot the proportion of pan identity switches in the test videos in this bar chart, and as we can see, video number 9 has more than 90% of identity switches as pan identity switches, and overall in all the videos we see that about 65% of identity switches are actually pan identity switches. So in conclusion, we see that offline methods with no linear motion model assumption perform well in broadcast hockey video tracking because they are able to handle minor occlusions pretty well. And the male culprit as far as hockey player tracking is concerned, as far as broadcast video is concerned, are pan identity switches. Thank you.
Great presentation, Kanav. So I think we have you online. So
Thank you.
what I'm very much interested in is, so I mean, we've now seen that these pan identity switches play a big role. But we've also seen that some of the companies like Sportlogic have multiple cameras. So have you thought of sort of the implications and how to handle these things when you go to multi-camera?
So as far as multi-camera feed is concerned, considering that you have multiple views of the ice rink, and provided there is a certain sync between all these cameras, and if you have access to the whole rink with this multiple cameras, then this problem will not arise because the camera is not panning and you don't have players entering into the camera field of view after a long time. But one way to address these kind of switches is to estimate the motion of players when they are not in the camera. For example, a player, he went outside the camera for 4 seconds. If we can estimate his trajectory based on what his previous appearance was, that can probably be one of the solution. But the solution of this problem is a pretty difficult problem, because since we don't have any observation and we only want to estimate the motion of this player when he's not visible, I would say it is a relatively hard problem.
Okay, yeah, thank you. So I mean, one of the things you ended up using here is using deep learning models. So can you provide some insights into sort of the added computation cost associated with using these deeper models rather than sort of simpler models?
Yeah, so as far as the training time is concerned, the training of these models takes time. Like there are certain models, for example, the fair MOT model, which takes almost 2 days to train. But the thing is, once these models are trained, then the inference time is not very much. Again, like the model, if it depends whether it's online or offline. An offline model would infer basically in a batch way. It won't give online predictions, but I would say the training time of this model, these kind of models, is pretty high. But once you have trained them, then the inference is relatively small. For example, it can process a whole video in like 5 minutes. And as far as video is concerned, like it can process, I would say, for processing a whole match, I would say it will take something like half an hour or something.
Oh, okay. And so in terms of, so I mean, in this paper, you sort of did some manual tagging. So if you would do this on a club basis, or sort of take your system and do it at a club, how much data do you think you would need to annotate before you would have sort of a good model for your team or your league or your arena?
Okay, so as far as an external league is concerned, so since we already have a model which is trained on NHL, if we have some other league which uses similar kind of a camera model, we will perhaps not need that much amount of data, because we can just fine tune this model onto the other league. So basically we can take this model, we can just fine tune this model. And for fine tuning, generally in deep learning, the phenomenon is that you generally don't require that much amount of data. If you have, for let's say, already have a task which does let's say face identification, so, or let's say image identification, so fine tuning it for another task which is not that different takes lesser amount of data. So I would say a data which is, let's say, 25% of the data which I already have would be sufficient.
Okay. Yeah. No, thanks a lot. In interesting work. Look forward to see more of it.
Thank you.
So let's thank Kanav. Next up, we have an exciting talk from a group of researchers. It's going to be presented by Adam Pilotte. He's a student at McGill University, where he also plays at the university team. So please, Adam, go ahead.
Hello, everyone. Thank you so much for tuning into our presentation on SARA. So SARA is an acronym for Scouting, Automated, Ratings, Analyzing Habits. We'll go more in details later, but before I get going, I just want to take the time to present all members of the staff that worked on the project, which compromises of myself, Adam Pilotte, Carleen, Markey, Mikael, Nahabedian, Katia, Clément-Heydra, Noah Chaikof, and Mairead. So what is SARA? So SARA, it's a tool to link video scouting to advanced statistics. And by scouting, we mean habits and events. So when we talk about events is the outcome of a play. So for instance, zone entry or successful breakout. And habits, we'll get more in details later, but it's basically how the player got there. So there's different habits, such as having the puck in the hip pocket or getting off the wall quickly, outside edges, etc. So why we decided to go on and do this project? So like our team compromises of people in hockey with completely different backgrounds, such as player, coach, player development coach, and people in the advanced statistics position. And we wanted to come up with a quantifiable tool for both player evaluators and player development staff to properly target different areas, events, and habits that a player needs to improve on. Sometimes, people in scouting and coaching position, they have such a large amount of people to look at and target different areas. And we really wanted to provide a quantifiable tool to help coach and scouts work with players. So ultimately what we came up with is two different SARA models, which can be used together, so intertwined, or they can be used independently, which is great. So the model one allows scouts to get data on the player's event, so like the microstat, like I said, the outcome of a play. and allows development coaches to get data on the players' habits. So it helps both the scouts and the coaches to better understand the player.
So basically, as we were saying, the goal of this project was to link habits to events and link events back to habits. But the first challenge that we faced from a statistical standpoint when working on this project was the fact that habits or micro abilities for different players are not something that are that easily quantifiable from a systematic standpoint. So when scouts are going to go watch different hockey games, they're definitely going to analyze habits that players have on the ice. But it's very rare that these scouts are going to think about quantifying these habits in a systematic way. And so with our team of players, coaches, scouts, and analysts, we first had to sit down and come up with a list of different skill sets or categories of skills which we were looking for, each of us in a different way, when watching hockey games. And so through discussion, we came up with 7 different skill categories or skill sets, which include skating, stick handling, puck reception, physicality, defending, passing, and finally shooting. Once we had those 7 skill sets, we went on our separate ways and basically this time had to come up with a list of different habits or micro abilities which would be related to each of these 7 skill sets that we had just identified. After each building our list, we came back together, sat on the discussion table, and merged all of these lists together to agree on approximately 30 habits which we were going to focus on in this project. In the bottom of the slide, you can see some examples of the habits that we ended up agreeing on. And if you want to get a comprehensive list of habits with the definitions, I invite you to either read our paper or you can also reach out to us. Basically, once we had agreed on the 30 habits to track, we had to find a way to quantify these different habits. And so the easiest way that we found to quantify these different habits were to treat them as binary categorical variables. Basically, binary categorical variables that meant that we were either going to assign the value of 1 or 0 to these different habits. And so to do that, we use the more likely than not criterion for most habits. The more likely than not criterion is revolving around the 50% plus 1 rule. And I can illustrate that with an example if you want. So let's say that in a given game, player A accesses or outside edges with ease 7 times out of 10 opportunities. For this player A in this game, the outside edge work habit is classified as a 1. Then let's say in the same game, player B fails to load the puck to her hip pocket 6 times out of the 10 opportunities where she has the chance to do so. For player B in this case, the hip pocket loading habit is going to be classified as 0. You might say that there is some subjectivity involved in the tracking process. And at the beginning, when we were building this idea, we flagged that as a potential issue. So when we were sitting and merging our lists of habits together, what was important for us to do was to not only clearly define the habits, but also clearly define what represented a successful performance, an unsuccessful performance, and an opportunity to leverage different habits. And by doing so, we were able to mitigate the risks revolving around tracking bias and subjectivity.
So once we have this habit tracking down, we needed a set of games to apply it to and some advanced stats from those games to link the habits to. The 2021 Women's World Championship was really a really great opportunity to do this because there was a really large player pool of elite players in a short span of playing games in a short span of time, which allows for a really robust sample that basically takes a snapshot of player ability in one point in time. So these players aren't like developing these various habits and various skills over the tournament because it's such a short tournament. And additionally, we had event level data available through Instat, which is a computer vision based company and hockey stats provider that tracks and compiles event data at the shift level. So we had some really granular shift level data for that, for stuff like accurate passes, breakouts via pass or stick handling, dump ins, dump outs, entries passing or carrying the puck, inaccurate passes, puck battles won or lost, puck recoveries and losses, shots blocked, Corsi for and Corsi against. So we have all these microstats down to the shift level data. Unfortunately, with data availability comes with some data issues that need to be balanced with the data set size. So going to the next slide, we can see that we kind of had three options to take a view of this, to look at this data at. We had shift level data, so basically stuff like accurate passes, normalized for each player shift, normalized according to their time on ice, and period level data, which is basically how many players or how many accurate passes does a player have in a period, normalized again to time on ice, and then same for game level data, number of accurate passes in a game. Unfortunately, all of these kind of came with their own issues. For instance, the shift level data, it doesn't look like there's anything on that graph, but there is. It's just like 20,000 data points of 0. So like players not having any accurate passes on a shift because shifts are really short and might be really long, and a pass might not even happen on a shift for a player. You have this really long tail going out to 1200 because again, this is normalized. So this really long tail and high number of low numbers is kind of present throughout the period level data and the game level data. And we ultimately ended deciding to go with the period level data because the game level data kind of reintroduced the noise that you can kind of see between the shift level data and the game level data, as well as it really didn't make that long tail any better, nor did it really get rid of or shift that had shifted into a normal distribution. So we decided to go with the period level data, which gave us about a little under 4,000 data points to work with. And each data point is a player's microstats summed / averaged over a period according to whatever microstat that might be. So taking the habits and the events, we can now link them, or we can try to link them under the SARA Model 1 feature selection framework. To go into this further, what we're trying to do here is take the habits, which are binary variables, and predict the continuous data, which is the events per 60. We decided to try out some, linear regression, random forest, XGBoost models just to, play around with this model framework first. And I kind of just fell on my face trying to work with this data. There's as we saw on the last slide, there's a really high number of zeros in both the event data as well as the habits data, because not all players have all habits. So we end up with some really sparse data, and the long tail end of the predictions, the dependent variable kind of messes with the model attempts as well. And the various models we tried really just couldn't capture the higher valued events. It would predict a lot of zeros pretty accurately. It would predict the first couple values of players that had accurate passes and predicted the player's number of accurate passes correctly up to 3 or 4 or something. But beyond that, it was kind of just a crapshoot. And we try to fix that with various things like a PCA and MCA, which is a variable decomposition. Basically, you're taking your 30 variables, 30 habits, and squishing them together in a statistically significant way. So you end up only with 2 or 3 variables to try to predict events on. Unfortunately, that also didn't work. We also tried something called Corex, which was a way of linking to sparse data sets and just dealing with the sparseness and as well as the variable decomposition. Unfortunately, again, none of these worked, and digging through the literature, basically what I found is that the only way to deal with this is really attempting a kind of smushed together data pipeline process where you use a classifier to predict the 0 values and the non-zero values and try to do regression to predict the relationship of non-zero values. Basically what the literature ended up saying was that if that didn't work, hope for a better method that comes down the line in 10 years. We could have tried something like a neural network, but that wasn't really in either of our wheelhouses at this point. So what we instead did, because there was some kind of relationship showing up with all of these various regression models that we tried, we pulled in the feature selection part of it. So instead of saying, okay, here's the quantitative relationships, we just kind of went like, okay, these are the qualitative relationships. We know that the regression models are predicting that stuff like edge work, outside edge work, feed in motion, getting off the boards. These are feeding into predicting puck battles in some way. Can't really quantify that super well, but we can use that in the frequency model that we'll be talking about in a minute. So moving into, say, the Sarah Model 2 framework, we now move to the reverse relationship, which is a much more normal relationship to try to predict. So like the continuous events per 60, the microstat predicting the habits out of those, which is a very simple classification problem, and basically predicting the probability of players exhibiting a habit based on those microstats. Just to address something that we got some comments on when we submitted this paper, we did try out some different models, such as the logistic regression, Random Forest, and XGBoost. All of them did really well. We just went with the Random Forest regression because that's what we went with to pull out the feature selection in Sarah 1, and also it just did the best when we were evaluating that. And you can look at our paper for more details on that if you'd like. So with Sarah 2, we end up just being able to make a prediction on taking these microstats, such as like breakout skip pass and dump ins and evouts and etc., and predicting all the different habits. And I should note that both for Sarah 1 and Sarah 2, we built an independent model for each kind of, for Sarah 1, we built an independent model for each event, and for Sarah 2, we built an independent model for each habit. So yeah, this is the success probability that we'll be talking about.
So now that we've explained Sarah models 1 and 2, let's talk about how they can be used and leveraged in a player development context. So back in 2021, Jack Han had introduced in one of his newsletter posts a player development matrix that was inspired by what Darryl Belfry was doing with the Toronto Maple Leafs. And so for purposes of this project, what we decided to do was to adapt this player development matrix to our project. So on the x-axis, for purposes of our project, in our matrix, we had the success probability, which is derived from the Sarah 2 model, as Carly just explained. And on the y-axis, we had the frequency, which is basically derived as the number of times a player gets the opportunity, or the number of events in which a player gets the opportunity to exhibit or display a certain habit. So in terms of filling up this matrix, the first quadrant that we have is the leverage quadrant, which are habits that players do often and well, and that they should continue to do and maintain in order to positively impact the game. Then we have the expand quadrant, which are habits that players could do more often in order to positively impact the game, as these represent habits that are low frequency but high success rate. In the red quadrant, we have habits which should be addressed right away because they are high frequency, low success rate. So these are things that players do often, but that they don't do really well. And finally, in the black quadrant, we have the development of habits, which are habits that players should focus on in the long run, as they are low frequency and low success rate, things that players don't do often, but that they don't necessarily do well either. So looking at a case study with a player that plays in the SDHL, let's see how this matrix can be applied for a player development coach. So looking at Vendula Pribilova's player development matrix, the first thing that we notice in terms of skill sets is that it's very probable that her puck reception skills are her main weakness. And so for a player development coach, digging in deeper and looking at the detail of this particular skill set allows to identify the habit of catching the puck in the hip pocket as a probable weakness that Vendula Pribilova should address right away, as it is in the address category, in the address quadrant. What's interesting here by quantifying these habits is that it allows different development coaches to be able to identify different points of improvement even before watching clips. So when they watch clips and they see these players play, it can allow them to tailor their development plans better to what they were expecting, and also allow them to be more precise in game situations to identify these weaknesses of different players. So finally, in terms of future work, what we could do with these models is to first compare habits to point projections to project players in different leagues, identify the difficulty of developing certain habits as compared to others, and identify also player archetypes based on different habits or different skill sets that blend together. Thank you very much for taking time to listen to our presentation. We now open the floor to any questions you may have.
Thank you. So we have Mikael and Carleen online with us. So welcome. Very interesting work. So one thing that I was sort of interested in was, I mean, here you can now look at scouting, development, etc., using these habits. But as a player, part of your habits come from what you're asked to do of your coach. So have you looked at sort of biases in these different teams and how you can separate biases on a personal level versus at the team level?
Yeah, that's an interesting point. I think that some coaches at the national team level have much more experience and much more knowledge regarding the technical aspect of the game. But overall, I would say that when players come in at the national team level, which was what we were tracking, there were they come from different club teams, and it's really in club teams, I would say, that you develop your technical skills. And at the national team level, since it's only a couple times a year or a couple tournaments in a year, it's more about the tactics. So it's more about finding ways to have all these players from different teams come in and play together in a tactical structure that makes sense for everyone. So at the national team level, I don't think that would be that much of an issue, even though there are some teams that may have better knowledge of the technical aspect of the game than others.
Okay, thank you. So we have an interesting question from the audience here. So have you thought about tying in game context in some way? So for example, dump-ins on the power play versus PK, or even strength?
Like on the modeling side?
Yeah.
Yeah. I mean, thought about it, yes, but actually implemented it, no, not yet. Just because this is quite a novel work and no one has really looked at something like this before. So I think that would be part of our like next step in this modeling process after, you know, we've gone through this process of saying like, okay, we can do this. Now how can we improve on it, and how can we use this as a jumping off point for even more interesting works. So I think that would be not necessarily part of this project, and but you know, a next step of it.
Yeah, no, interesting. I mean, I would be interested to see, or maybe I ask really quick. So have you scaled the variables before you? So I mean, you had this long tail. Did you scale the variable before you tossed them into the machine learning and PCA analysis, etc.?
They were normalized, yeah.
Okay.
If you want to take a look at it, as you mentioned, it's on the GitHub. But yeah, I tried all sorts of things with those variables, but it was quite difficult to work with. I will say so.
Yeah, no, good stuff. Yeah, but I mean, given the long tails, it seems like a good thing to do. But yeah, interesting work. Thanks for presenting. So I think now we're gonna close this first half of this session, and the plan now is that we're gonna take a short break. So we're gonna be back at 16:45 or 4:45. But I hope to see you soon. We have 5 really interesting research papers left, and hope to see you then. Bye. Welcome back to LINHAC, or Linköping Hockey Analytics Conference 2020 or 2022. So we're in for a continuation of a really exciting research program. So we started before the break with 2 papers. After the break now we're going to have another 5 research papers. For those that missed the first part, these papers are selected by an international program committee that I chaired, where we had people, researchers from around the world, reviewing these papers, giving feedback on them, and selecting 7 papers in total. Now, these papers that we ended up selecting were from Sweden, Canada, USA, and Switzerland. And with that said, let's hear some exciting research. First up, we have Ulf Johansson. He's a professor at Jönköping University here in Sweden. So please, go ahead.
Hello everyone, I'm Ulf Johansson, and I will present the paper How Analytics is Changing Ice Hockey. And this is joint work with Erik Wilderoth and Arsalan Sattari, and we are from Jönköping University in Sweden. The outline: first, a short background from other sports, in particular baseball. Then we will look at the Corsi development in NHL and SHL. After that, adding expected goals to the analysis, comparing what we call the Corsi and the XG eras, and ending up with some concluding remarks. Starting with baseball, it's easy to think about the Moneyball revolution as just a tool for scouting and player evaluation. But the data-driven approach has actually changed the way baseball is played. For instance, there are now significantly fewer stolen bases and sacrifice bunts. And the reason is that analytics showed that even a successful sacrifice bunt often reduced the expected runs in an inning, and that for attempting a stolen base, the chance of a success must be extremely high. We can also look at what is called a defensive shift, and the most typical shift is when there are 3 infielders positioned to the right of second base with a lefty batting. This was a rare positioning if we go back to 2010, with altogether just 1,700 defensive shifts in the entire season. In 2019, there were more than 25,000 defensive shifts. From another perspective, we can see that pitchers are now looking for more strikeouts and batters for more home runs. So both home runs and strikeouts have increased dramatically. And as a consequence, the number of plays where the ball is actually put in play has decreased. This is a view from basketball, and we can see that analytics here has absolutely changed the way basketball is played. So if we start in the left part here, we see the shot locations from 2006 and 2007. And we can see that a lot of shots are taken from many different positions. In 2019-2020, however, we see that shots are now either from very close range or for 3 points. Going to ice hockey finally, we will use first the metric called Corsi, and I know that this is well known to everyone attending, so I will not go through it here. In this table, we compare Corsi percentage in the regular season to the regular season finish as a kind of predictor for success in the playoff. And what we can see here, so here, just to explain the numbers here, it says that first in this column here, we see the champions, the Stanley Cup champions. So here we see that Detroit are the champions, and they actually both finished with the best regular season record, and they had the highest Corsi percentage. But if we mow down this column, we see that the champions very often had one of the best Corsi percentages. And if we look here, we see the same thing, but from another perspective. So here we look at the end of road finishing for the best Corsi percentage team. And here we can see that again, Detroit were the champions. In the next year, Detroit were the runner-ups. Chicago were the champions, etc. Actually, there is a fairly sharp line here where we can see that the pattern is very different from the 2016-2017 season. If we look at the numbers here, and we can also see that the best Corsi percentage team didn't even reach the playoffs here. Doing the same analysis for the Swedish Hockey League, we have a very small sample size, just 4 years. And we should also remember that there are fewer teams in the Swedish playoffs. However, we can see an interesting pattern where the best Corsi team also became the champions in 3 years out of the 4. And this could then be compared to, for instance, the regular season winner, which could end up as the runner-up or in the quarterfinal once they were the champions, but then they were also the best Corsi team. We can also look at the development of Corsi over time, or rather the number of shots in a game. And if we start with NHL to the left here, we see that there is a small but steady increase in shots over the years. In Sweden, it is actually fairly stable, and in the last few years, there is a small decrease in the number of shots. To further look into this and to compare Corsi over a number of seasons, we categorize the teams into 4 groups, and we have the groups here. So we call them dull, which means a low Corsi for and Corsi against, bad, good, and fun. And what we can see here is that we have a clear movement from the top left part to the bottom right. And this means then we start with a lot of dull teams here, and there is actually no team that was categorized as fun. And then we get more and more fun teams. And actually in 2018-19, we don't have a single team categorized as dull. Then there is a small reaction to this in the last year here, 2019-2020, where we again have 3 dull teams. Going to the Swedish Hockey League, where we only have 5 seasons, maybe the most interesting observation here is that we actually have a movement to the top left quadrant. So in 2019-2020, we have a lot of dull teams here. We now introduce expected goals in the analysis. And what we can see here, where we have the blue line represents the expected goals, and the red line is then Corsi. And what we can see is that we have more and more shots to the 2010 and 11 season. And after that, the quality of the shots actually decreases from 2011 to 2015 and then increases again. And we argue that this is actually one of the most interesting results in the study. And we say that this represents the rise and fall of the Corsi game. So typically we have the rise of the Corsi game here, and then here the quality of the shots become more and more important, and we see that that we now have higher XG, making it more important than Corsi. Here we make an outright comparison between the best Corsi team and the best XG team. And to do this, we use a scale where the Stanley Cup champions get 5 points and then all the way down to 1 point. And of course, this is a slightly ad hoc analysis, but still, if we do this in what we call the Corsi era, so including the season 2014-2015, we can see that the best Corsi team got 3.25 points on average, so meaning that they ended up better than the conference final on average. And this could then be compared to the regular season winner that got on average 2.75 points and the best XG team with 2 points. In the XG era, however, so that would be after this season, we can see that it's actually the best XG team that got the most points. So not as high as 3.25, but 2.8, and this could be compared to 1.2 and the regular season winner 1.8. So in this era, being the best Corsi team is just slightly better on average than getting eliminated in the first round of the playoffs, while the best XG team is almost on the level of getting to the conference final on average. Having said that, it could be interesting to investigate where does the higher quality of the shots come from. And this is really outside the scope of this study, but we noticed a few things. And first of all, there is a significant increase in the number of one-timers. And also, as we can see from this picture, although it's not that clear, but here it's just for 4 teams. For the full image, you could look at the paper, but here we can just compare where the shots are taken in 2010 and in 2018. And again, the picture is not that clear, but what we can see is that the shots are taken from a closer range, and in particular, they are more centered. So if we compare, for instance, this picture here to the picture here, this is a fairly common pattern. To conclude, we have in this paper described how advanced analytics has influenced ice hockey, and we identified 2 very different eras, what we call the Corsi era and the XG era. And in the Corsi era, the teams strive to take many shots, resulting in that the overall number of shots increased, and especially in the NHL. In the last 5 years, however, the quality of the shots as measured by XG has become more important. And the logic behind this was confirmed by comparing the playoff success of the best Corsi, XG and regular season teams. And for many years, we could say that the best Corsi teams did in fact also have the most success in the playoffs, but now this position is actually taken over by the best XG team. And with that, I finish the presentation. Thank you for your attention. I will be happy to answer questions now or offline. You can find my email here. Thank you.
Thanks, Ulf. So very interesting talk. So Now the plan is that we're going to take another paper from the same group. This one is going to be presented by Erik Wilderoth, recent champion with Färjestad as well. So please go ahead. Let's listen to Erik.
Hello everyone, my name is Erik Wilderoth and this is Where Not to Lose the Puck, written alongside with Professor Ulf Johansson and postdoc Arsalan Sattari, Jönköping University. At first I want to apologize for my voice. I guess this is the voice of a Swedish champion and this is how it goes, but I will overcome and I hope it doesn't distract you too much from the paper. This paper is about controlled versus uncontrolled plays. In our domain, in our analytics community, it's of course fairly known that controlled plays is something good and uncontrolled plays is uncontrolled. But with the new data we have, with the more detailed data, I want to dig into what actually happens. Where is it dangerous to lose the puck and risk reward? Making a controlled play versus an uncontrolled, what is the risk with doing that and the reward gaining it down? And therefore, see some good tendencies in the game. First, some terminology for those who doesn't do this on a daily basis. That when I speak about exits, uncontrolled, I will talk about dump outs. You exit your defensive zone to the neutral zone and you're just throwing the puck to the next zone there. Basically, if you do it by control, I mean that you do a carry out with the puck or you pass a teammate. And the same goes along with entries to the offensive zone. Either you dump it in or you pass it or carry it in. Control was uncontrolled. That's the definition here with the paper. One of the most famous plays in Swedish ice hockey is Björn Melins in Game 7 2016 finals between HV71 and Färjestad BK. For those who doesn't live in Sweden, I will just talk fairly short about it. We have Björn Melin here trying to 1 minute before this play. It's important to know that Färjestad BK tied the game with 1 minute to go. And everyone is just anticipating the overtime, waiting for it. Björn Melin has made one dumping before this play. Pelle Gustafsson made another 2 players in HV71. And then when they have the third chance to do a dumping with 10 seconds to go, Björn Melin tries to do a deke and make a carry, fails, and Färjestad makes a turnover. Scores with 7 seconds to go and goes to the finals. Björn Melin was very regretful after the game, of course, with tears in his eyes. He apologized to players, fans and all that. I wanted to win the game, then I make a mistake that I must not make. For us CSV nerds, instead of a dumping, I tried a carry. I failed. This paper, we will look into the numbers. Did he make the wrong play or the correct play by the numbers? Let's see. But just the data I've been looking into, it's possession changes. And by a possession change, I mean Team A has the puck. They have it some time, then Team B steals it, and then we will look into this possession. What happens after a possession change happens? Maybe they score, maybe it turns it back over to Team A, and then it goes back and forth. A game in Sweden has about an average of 244 possession changes. We have quite a lot nice data with Sportlogic for 3 complete seasons. It's only 5-on-5, and I have filtered out data that is the possession change is less than 1.5 seconds, because it seems that a lot of noisy data when you come down to that small span of data. We have rebounds, a rebound can be marked as a dump out in the data and so forth. So I have excluded that. 1.5 seconds is So threshold is set by me by just watching a lot of possession changes and see that beneath that it's more of a reaction and noisy data than decision by the player. So we filter that out. Just as some small takes on team strategies in Sweden, dump out rate is averaging about 23% within this data set. This graph is the teams of 2021 season. We have Skellefteå AIK here, the kings of control plays, both exiting the zone, dump out rate, but also entering the zone. They made everything with control in a way that no one was close to. Frölunda is another team that is famous for having a low dump out rate by a fairly higher dumping rate. On the other side of the graph we have Malmö, Linköping. You can't say really much. HV71 was relegated that season to Hockeyallsvenskan, and yeah, you can see they are the most average team. So, but there are completely different strategies how to play the puck, obviously. If we just dig into the location of the puck drop by zone, it's by no surprise the closer you are to your own goal and losing the puck, the more goals we get against. And you can see here the turnover rate for goals is 0.75% in your when you lose the puck in your own zone. If you lose it in the offensive zone, it's 0.4. The time is not that big difference actually, and that of course makes sense because when you lose it in the offensive zone, it gets to a turnover. By here you can get a cycle play against or something like that. So yeah, no surprises really, but the defensive zone has the highest. But here it gets interesting where we dig into the location of the puck drop. Really, the location of the puck drop by making smaller zones. The central side of things is the most dangerous, as it seems. 0.7% of all pucks drops in the central part of the ice. Turns over to goals against. No surprise really, the most dangerous place is right in front of the goal. Why it's not here? I don't know, maybe it's easier here. So a lot of goals from here was outfiltered, but the threshold I was set by 1.5 seconds. Maybe that's a reason, but this is the most dangerous place to lose the puck. But if we look just by the x-axis, we can see that behind the goal is actually more dangerous than in front of the goal. And I would say that it has a lot to do with the strategy in Sweden with the forecheck. It's a big strategy here, and it seems to pay out. It's quite good harmony in the data, we would say. We have the further we get from the goal, the numbers go down, 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 down. But here, at the offensive low line, we have a small bump in the data. We have here to the very bad zones to lose the puck. We can recall Björn Melin's puck drop was, I would say, here. So it was a really bad place to choose to lose the puck, because it was really a choice. But yeah, but it's kind of interesting that not more possession chances actually ends up in a goal against. You have like 1 in 200 by losing it here. It's not that bad odds, right? But if we look, now we looked at the location. If we instead switch over to the type of plays, what is actually the most dangerous play in ice hockey? The dump out, it seems. If we break it down by type and subtype, we have zone exit and zone entry. We get interesting data here. We have, first of all, we have carry out at 0.43, and that's the same as control entry. So it's as dangerous to entering the zone we control that exiting the zone we control. It's kind of interesting, and pass is higher turnover rate goal against than carry out, and that makes sense because you're not in the location as the same location as the puck is. When you drop it here, maybe we will have a higher penalty rate or something when you have a carry out fail. But the dump out is, as I wrote, the most dangerous play actually. And if we break that down one further step, we have some subtypes to the subtype. We have when it's a minus after, it's a failed one. And you can see it here, fail, 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 and then we have plus, plus, plus. The failed one is above 1%, and the failed dump out is actually quite much higher than the rest of the plays. That's interesting, right? I would say that I wouldn't anticipate that, but that's how it is. And with this new knowledge, we will look into what happened last. It was 3 weeks ago. We had the finals in Sweden. We have the overtime in game 4 between Luleå and Färjestad. It's an important time in the series. Luleå is in the lead with 2-1 in games. It's 4 minutes into the period overtime. Luleå in yellow overturns the puck. They're gonna exit the zone. And with our new knowledge and by the timing of this video, I guess you can guess what will happen. Linus Fröberg gets a puck and he decides to do a dump out. He fails. Färjestad take the puck deep, put it into the inner slot, scores, bam, game over. Series tied to 2-2, and in the end, Färjestad will win the series and become Swedish champions, and I will get the voice that I have. But that's history, right? So if we put this on a risk-reward scale, I borrowed some figures from Thibaud Chatel. Figures are from the Swiss league, so it's not perfect, this data set, but we have in red, we have the entry plays, and in blue we have the exit plays. And we can see on a risk scale, we have the goal percentage against, and on a reward scale, we have gaining XG by doing a play. By the entries, it's quite obvious, and it's quite what we would expect, I would say. Jumping has the lowest risk, but control is gains almost the double figure in XG. So yeah, I can't blame someone in lead in the end of the games that actually makes the dump-ins instead of control plays if you just want the time to go and nothing should happen. But the interesting part is the blue one, the exit one, I would say, where we have the dump out that has the highest risk and lowest reward. Pass and carry out almost have the same reward, but the pass has a lot higher risk. With that in mind, we can go back to what we started this this paper with, or this presentation. Did Björn Melin make the correct play? And by the outcome, obviously he didn't. 10 seconds to go, his legacy will always have the watermark of this play. Just Google him and you will see. But it wasn't, by the numbers speaking, the risk shouldn't have been that high that it was, but if you go back to watch that actual play, you can see that his teammates is really doing a horrible job of supporting and carrying. He should have passed the puck or just dumped it in, but I would have gone for the pass if you wanted to win. That would have been the best play, but in slow motion 16 years later. It's quite easy to be Mr. Obvious, right? But yeah, but the other part of it, if we think about the Lulu player, he added the same risk in that play, try a dump out in that situation, and it failed. But his legacy is not destroyed. It's not even disturbed, I would say. It's that's kind of interesting. If it's easy if you would make this risk and reward scale of how media would treat you, then Tampa would have the lowest risk, right? But with this data, it's actually the worst play he could have done, and it turned out as it does in like one of 75 plays with a goal against. So with that in mind, I hope we have learned something about risk and reward and how we even want to make more control plays, because it's not that dangerous as we think, and it's actually a good way to limit the opposing team's chance to score against you even when you're in lead. You shouldn't start to dump the puck zone to zone, would be my suggestion. And that was it for now. I hope you will read the paper if you want further details or ask me questions later. Thank you.
Okay, thanks a lot. Very interesting presentations, and we now finally have both of you online. So welcome, Erik and Ulf. After some technical difficulties, it's good to see you here. So I thought we discuss both papers as in one package, but we can start with the second paper. So I mean, after seeing the video, I was tempted to see if we could get Björn Melin online and get his take. So I mean, this risk-reward thing seems sort of convincing, but do you think that it also comes down all the way to an individual's decision, or is it more a tool to be used at a team level that, okay, our strategy is that we want to do this type of zone entry, rather than saying that a player did the right or the wrong decision?
I would say often the play that the player actually do is the design of what the team try to do and what the teammates has put into. So it's more about strategy from the team, I would say, and getting the structure before to set up players to do good plays. If you are put in a position where you have to make a dump out, of course, most players want to play creative and do nice carry-ins or carry outs or so, and not dump outs. But if you're put in a position where you think that you want to minimize the risk against players, do dump outs. That's what we're taught to do.
Yeah, no, good point. Yeah, so one thing I wanted to sort of get to there was, like, if you take this particular Luleå player, for example. So in the statistics, we don't have anything that say how many options he had, for example. So in the Melin case, he has options. In some cases, he can dump in, but in some cases, when we come to a dump out, all the passing lanes are taken. So have you thought of sort of taking passing lanes and those things into account to sort of even further sort of, I mean, you dug fairly deep into it, but sort of taking this analysis one step further to take into the conditions of each player and the situation?
Yeah, I understand what you're getting to, but we don't have that kind of data for the moment. I would love to have that, so we could measure decision making on the players. That would be great to see if he made the best decision out of the number of choices he did have. We don't, and of course we lose context with this data. So it's easy to cherry pick some goals here and there. I did that in this case as well to prove my point, but that would be really good and nice next step for the paper for sure.
Yeah. So I mean, to sort of give us segue to a later paper in this session, and I think as a team analyst, you probably will at some point have access to this. I mean, that's the tracking data. Where you so in the last talk we'll see where you sort of take passing lanes into account. So if we now gave you that data today, what would you be on your wish list in terms of analyzing using this type of zone entry and zone exit type statistics?
Yeah, this would be very good feedback for a coach, even for players to go down to even see that that we can measure decision making and then break it down by plays. That in this play you had these three options. The pass would be the best option. If you look in the numbers. Why didn't you do that? When it's so easy, we can see it here that you would raise our expected goals by 2% or something like that. But yeah, we could do a lot with that kind of data, I would say. And I think I would keep it first within the team to secure a second championship, and then we can present it here.
Okay, so we won't be looking forward to a LINHAC 2023, but maybe LINHAC 2024.
Hopefully 23.
Yeah. Oh, okay. Yeah. No, that sounds good. Sort of a more technical question. So you had this threshold of 1.5 second. So did you play around with that threshold, and similarly, did you play around with any thresholds for when the situation were sort of over, so that we don't take 30 goals 30 seconds later or something like that?
Yeah. There are not many plays that have like that. I think I found like one sequence with 13 passes within the team. That was the most for 3 seasons. So there are not a lot of possessions that is that long in ice hockey, which is kind of interesting by itself. By 1.5 seconds, it was a lot of eye testing, I would say. I tried 1 second and tried 2 seconds. And then I looked in everything in between to identify, and 1.5 seconds seemed like the best threshold by the eye test.
Yeah, no, sounds reasonable. So for those that perhaps, I mean, we hear a lot of AI and machine learning and those things, and it's easy to think, well, okay, we just give machine learning, and often there's sort of this the trained human eye that need to be in there as a cookbook. So no, seems reasonable and well justified. So let's go to the first talk. So here you talked about how analytics is changing ice hockey. So apparently analytics help win Swedish championships. So congratulations. But here you showed some comparison with basketball also, where you saw these very clear sort of patterns in shot maps, etc. And I wanted to listen a little bit in terms of if you could sort of go into the data and see, okay, this transition between the course era and then you move over to the expected goal. What behaviors do you think that were sort of the reason for that?
Yeah, so Erik, please add to this if you want. But I think where we started this was just by saying that, I mean, teams and players became aware of that Corsi was used as a metric, and then they started to shoot more. But at the same time, the success of this Corsi metric was kind of backed up by the results. So typically the best teams in Corsi also advanced, in the playoffs. So that was like the starting point.
Yeah. No. So yeah. Please go ahead, Erik. Did you have something?
Yeah, I can just take it to the next step because we could see that Corsi was rising and everyone started to shoot, and then after a while, when everyone is shooting a lot, not all teams win in any way in case, but then you start to think about what kind of shots you are taking, and we could really see a really big race of one-timers, for example, since 2015, and that's one kind of shot that is, I think it multiplies by 3 compared to an ordinary shot in XG. So teams were first looking into Corsi and then thinking about the quality of the shots actually, and that of course makes sense.
Yeah, and I mean to some extent we've seen that say in NHL where the teams are trying to get the puck to the inside to a larger extent. In terms of measures that currently doesn't exist, in that might be sort of patterns that you think would be interesting to see how they increase the quality of the shots. Do you have some ideas or insights that are things that we in the analytics community should be searching for?
I think it's a dangerous road to go only for the high quality shots. We have seen teams in Sweden try to do it. We saw that HV71 was one of the teams that had improved their quality per shot the most, but their Corsi decreased the most. And also Brynäs last year, and they were the 2 worst team in the league 2 years ago. So I think it's a mixture of it's hard to get high quality shots without the quantity.
And there are, of course, I mean, there are different ways of calculating XG, and I mean, all of them more or less are then well calibrated with actual goals if you look at it from an entire season. So I think, I mean, you could devise more sophisticated XG models taking into account where all the players are and I mean the time that the player has had the puck in possession and things like that. But then again, on the season level, it is already fairly well calibrated.
Yeah, no, good point. Yeah, so I mean, hockey is a game of sort of a combination of skill and chance. And with these sort of things, you're betting on your probabilities. Unless you're shooting a lot, it doesn't matter if you have 90% probability. But if you would say, in terms of not all teams are equally skilled. So did you think anything about what differences you might suggest in terms of where in this sort of shooting lane? So I mean, you had this where you had team 1 to 30. So did you look at sort of ranking them from the best team to the worst and see if it sort of differed in their behaviors?
I didn't do that. Did you? No.
No, we didn't. But what I can say we have seen is SHL teams that outperform their XG tends to shoot further and further away. So you get more and more confidence in your shooting ability, and then backing out from the goal. I think you can score from anywhere, and then you're not outperforming the XG anymore. So I think you can see it both ways. That teams that are good first may become bad because of their overconfidence or something like that.
Okay, really interesting work. Look forward to the follow-up works in future years. Thanks for sending and talking to us. So we're going to move to the next paper. So here we have a paper from Simon Fraser University in Canada. We're going to have Brandon Kumagai and Ryker Moreau and Kimberly Kroetch. Please take it away.
Thanks, Patrick and Nicholas, for organizing this conference and having us here today. My name is Brandon Kumagai, and I'm going to be presenting with Kim Kroetch and Ryker Moreau on our work entitled Predicting the NHL Draft with Rank-Ordered Logit Models. To kick things off, let's start with a motivating example for our work. During the 2021 NHL draft, the Dallas Stars were on the clock with the 15th overall pick, but rather than making a selection, they traded down from 15 to acquire the 23rd, 48th, and 138th overall picks, where they selected Wyatt Johnson, Artem Grushnikov, and Jack Barr, respectively. In retrospect, the main player that stands out in this trade is Wyatt Johnson. When Dallas picked him 23rd overall, it was thought to be a bit of a reach by draft experts. However, a year later, Johnson is looking to be an excellent pick, as he followed up his draft year with an exceptional performance, leading the OHL in scoring. Let's assume that Dallas really believed that Johnson was a star in the making prior to the draft. The goal of our project is to estimate the probability that a certain player will be available at a certain pick, given the set of players already selected. For example, this plot shows the probability that Wyatt Johnson will be available at any future pick, given the players selected from 1 to 14 are off the board. When Dallas was up with the 15th overall pick, there was a 100% chance that Johnson would be available to them. But by their next pick at 47, this chance drops down to just 88.7%. If they believe Johnson is going to be a star, they probably wouldn't want to take that risk, even though it's not too large. However, by trading down to pick 23, their chance of getting Johnson only drops to 99.3%. And in addition, they obtained 2 extra picks in the process, making this trade a low-risk, high-reward transaction. Now with a bit of motivation behind how this model can be used, I'll pass it over to Kim to discuss exactly how it works.
Okay, so to model the NHL draft, we're using rank-ordered Logit models. And these have been previously employed in multi-competitor sports, where the outcome is the rank ordering of the players according to their performance in the sport. For example, Tyrell Stokes, who inspired our work, modeled the ranking of runners in the 100-meter dash, as shown here on the right. The goal is to predict the probability that a certain contestant will place in a certain position, given the entire set of athletes. There are 2 key quantities to discuss. Theta I is the underlying ability of athlete I, such as their running ability, and Yi is the athlete's actual performance in the competition, such as their time to complete the race. We applied these ideas to the NHL draft setting, where the outcome is the order in which prospective players are drafted. I'll talk about theta and Y in the draft setting a bit later on. Each year, there is only one NHL draft from which we can obtain a rank ordering of the players. To obtain more data, we use publicly available prospect rankings provided by draft experts, such as scouting sites, media outlets, and reliable blogs. We refer to each of these experts, or team of experts, as an agency, and refer to an agency's prospect ranking as a ranking set. We have 54 ranking sets for the 2021 draft and 44 for the 2022 draft. As an example, we have displayed on the right a ranking set from TSN's Bob McKenzie for the 2022 draft. To give an intuition behind the model, imagine there are only these 4 prospects, and let's say that we know their theta values given here, where higher theta values correspond to higher skills. The draft consists of a series of player picks. We model each pick with a multinomial Logit model, which uses the abilities theta to produce selection probabilities pi through the formula shown in the middle. Consider only the first pick. In this example, the model gives a 97% chance that Wright will be chosen first. To consider the probability of the entire draft result, we use a series of conditional multinomial Logit models, where on each pick, we condition on every already drafted player being removed from the pool of prospects. So let's assume that Shane Wright was chosen first. To model the second pick, we remove Wright from the pool of prospects, and then the selection probabilities for Cooley, Slafkovsky, and Nemec are then updated to account for Wright being removed. Now let's say that Slafkovsky was chosen second. We repeat the process, remove Slafkovsky from the pool of prospects, and recalculate the selection probabilities. Here we obtain selection probabilities of 81% for Cooley and 18% for Nemec. Choosing Cooley on the third pick leaves only Nemec, who must then be chosen on the fourth pick. The final result of this pretend draft is shown here, where Shane Wright was picked first, followed in order by Slafkovsky, Cooley, and then Nemec. The probability of this entire ranking set is found by taking the product of the selection probabilities for each player that were updated at his corresponding pick. And this can be written through this formula here. In our example, we find a 26% probability of obtaining our ranking set given the player abilities. So our goals are 1, to use Bayesian inference to estimate posterior distributions for each player's theta I, and 2, to use these distributions to repeatedly simulate the draft. From these simulations, we can estimate the probability that a certain player will be chosen at any particular pick, given the already drafted players. In the draft context, theta I can still be thought of as the player's ability, and yi becomes the underlying evaluation of the player by the agency. So we can imagine, for example, that the agency assigned each player some score out of 100 in order to rank them. To obtain the selection probabilities described previously, a key assumption is that conditional on the player's ability, theta I, the underlying evaluation yi follows a Gumbel distribution centered at theta I with scale 1. And this produces the likelihood shown at the bottom. Let's denote the number of ranking sets by big K and the number of players in ranking set K by mk. If within each ranking set we index the players from 1 to mk in the order of their selection, the likelihood can be written in the form on the left-hand side as the product across all ranking sets of the probability of observing that ranking set, given the abilities theta. For ranking set K, we can write out this probability term as the product of the conditional selection probabilities, as demonstrated in the example with just 4 players. So that sets up the foundation of our model, and now Ryker will discuss some additional extensions for the draft case.
Thanks, Kim. Now let's move on to some extensions of the rank-ordered Logit model that will be useful in our application. We have seen earlier that each player's probability of getting picked, pi I, is given by the following equation, but we only looked at the simple case of 4 players. What if we observe a ranking with these 4 players? However, there's a larger pool of players that could have been chosen from. For simplicity, let's say that there was a pool of 6 players, but the agency only ranked the top 4. For this case, we can change the summation in the denominator to big M, which now represents the entire pool of players to select your ranking from, even if you do not use all big M players in your ranking. This extension will be important in determining a final ranking since the players and number of players in each ranking differs. The change in the likelihood is fairly simple. The probability of any K ranking is now the probability of y1 greater than y2 greater than up to ym, and that has to be greater than the max of the remaining players, ym plus 1 up to y big M. This is conditioned on all theta values from 1 to m, and as mentioned in the last slide, the summation in the denominator of the probability equation gets changed to big M. For our next extension, we will look at how rankings change over time, or in the application of the NHL draft, how rankings change over the course of the season. First, let's look at an example. Aatu Räty was a top prospect in the 2021 NHL draft. Near the beginning of the 2020-21 season, Räty was considered to be a possible #1 overall pick. However, if we look at the rankings as the season went on, we see the average ranking from the agencies is around the 20th pick as we approach draft day. Obviously, we should put more merit on rankings closer to the draft. So how can we deal with these changes over time? Examining the 2022 draft, we split the season into 5 sections, corresponding to major events such as the start of the season, the World Junior Championship, and the end of the season. Looking at each time period, we can note a few things. First, the preseason will be used to inform our priors, as that is the start of our ranking data. Next, the middle 3 periods are considered to be the meat of our model, since this is when the majority of rankings come out. And lastly, due to the timing of our analysis, there is insufficient data coming from the postseason rankings. Therefore, we will not consider this time period in our analysis. As we progress over the time periods, we will use a Bayesian autoregressive process on the ability parameter. This process is used to obtain a theta value for a time period t plus 1 by taking the current theta from time period t multiplied by an autoregressive parameter nu and adding the parameter delta t plus 1, which comes from a multivariate normal distribution. We will dive deeper into the estimation of these parameters a little later on. For each individual agency, we visualize the cutoff points for each time period in the given plot. The auto ranking was adjusted to be in a certain time period if that agency already had a ranking within that period. The first time period was used to inform our priors due to the lack of rankings, and like I mentioned earlier, we see that the meat of our model really came from time periods 1, 2, and 3. Using the likelihood from the unranked players extension, we added an additional level to involve the differing time periods. We do this by adding a subscript t to the ability and performance variables throughout the likelihood. With this, we also have to add another product, which takes the previous likelihood and takes the product over time periods t equals 1 to t, big T. We now have the full likelihood that we will use in our model. As mentioned, we use a Bayesian approach in our model. The full details of how we obtain the posterior draws are explained here. The distribution of time period 1 is multivariate normal with mean mu and variance covariance sigma. We obtain mu from the preseason data, and sigma comes from an inverse gamma distribution. We then progress through the time periods as stated previously with that autoregressive process. The priors on those parameters in the autoregressive process are as follows. So we have nu from a uniform distribution, and tau is from an inverse gamma distribution. On the right, you can see how the ability parameters change over time. We can see that the ability parameters adjust from time period 1 to 3 to represent the changing opinions of agencies as the season progresses. This entire process allows us to have up-to-date, accurate posterior draws without losing any information from early in the season. Now I'll send it back to Brendan to discuss our results.
Once we obtain these posterior draws, we can take the player abilities in the last time period and use them along with the selection probability equation that Kim mentioned earlier to simulate the outcome of the draft. Using these simulations, we can obtain cool results from our model. First up, we simulate the outcome of the rest of the draft after every pick to estimate the probabilities of each player pick combination occurring. As an output, we get this cool GIF inspired by Brian Burke and the analytics team at ESPN with their draft probability tool. Let's run through it again and stop after pick number 5. Here we can see that the probability that William Eklund is selected in the next 4 picks is extremely high since he's the best player left on the board. Whereas if we look down the board and look at someone like Scott Moreau, who's generally ranked in the 2nd or 3rd round, he has a very wide range of pick probabilities and is very highly unlikely to get picked anytime soon. Looking closer at the 2021 and 2022 drafts, this heat map allows us to see some cool patterns in each unique draft class. For example, we can see the natural tiers form in the draft using this model. In the 2022 draft, we observe large drops in pick probabilities between Shane Wright and Logan Cooley at 1 and 2, Matt Savoy and Danila Yurov at 7 and 8, and Liam Ogren and Philip Mazar at 18 and 19. Additionally, it's interesting to compare between these two drafts. For example, we can see at the top of the draft that there's a lot more uncertainty in the first overall pick in 2021 as opposed to 2022, where Owen Power has roughly a 40% chance of going first, while Shane Wright, on the other hand, is a bit more of a slam dunk at 95%. While this heat map allows us to get a big picture overview of the draft, we can also visualize these probabilities on a player-by-player basis to inform strategy. For example, the New Jersey Devils have reportedly been shopping the number 2 overall pick in the 2022 draft. 2 possible options at the spot are Logan Cooley and Juraj Slavkovsky. Suppose a team with the 7th overall pick is interested in Slavkovsky. They can use this probability distribution to see that there's only about a 12% chance that he's going to fall to them at 7, which can in turn help management decide what assets they're willing to give up in order to acquire that 2nd overall pick in trade negotiations with New Jersey. So these are just a few cool results from our model that we're happy to share with you. We believe that this rank-ordered logic model provides an excellent foundation to predict the NHL draft, but there's still a lot of areas that we feel like we can improve upon with this work, such as incorporating a covariance structure to account for team needs and team and agency tendencies, addressing the correlation between ranking sets by partnering agencies such as, say, TSN's Bob McKenzie and Craig Button, sharing draft notes and potentially influencing each other's rankings, and also conducting deeper model evaluation techniques to find the weaknesses in our model and improve upon it. And that's everything that we have for you today. Thanks so much for listening, and we're excited to listen to the rest of the conference.
Thanks a lot. So very interesting talk. So we have Brendan and Kimberly here. So welcome. So I very much enjoyed this talk. Have sort of being interested in probabilities and these type of models myself. So I was a little bit interested in sort of the data collection, getting this type of data set. How did you go upon the scraping websites or getting all this domain knowledge?
Yeah, so that was a bit of a mixture between scraping websites where we could. Then some websites didn't really have like a nice, easily scrapable format. Like some of them posted a picture of their rankings or a picture of an Excel spreadsheet. So we had to go through and manually scrape some of those. But for the most part, like whenever we could and whenever we found kind of nice formatting in whatever, if it was a text document or a table, we would just scrape that using Python Selenium.
Oh, okay, thank you. So now there are a few sort of different type of rankings out there, but there is also these sort of pretend drafts. So you mentioned Bob McKenzie, etc., and the people at TSN. So I mean, they sit together and say, okay, this team needs this type of player, this team needs this type of player. Would it be difficult to take those type of things into account to further improve my probability to have my player available in round 1, my player available in round 2, etc.?
Yeah. So, oh yeah, Kim, go ahead.
I was just going to say that's sort of what we were getting into right at the end as future work is we want to, like, so right now we just have for one player, we have their underlying ability parameter theta, and we're sort of leaving that just open, but we want to later incorporate a covariate structure for theta. So then we could include both like team level predictors, like what kind of skills they are looking for or what position they need on the ice, and also player characteristics like their height, their weight, or some measure of their like points or something like that. So once we incorporate those into the model, then we'd be able to adjust those kinds of things.
Oh, okay. Yeah, no, looks like an interesting future work. So I have a question here from Tim. So I would guess that across different agencies, there is reasonable agreement, correlation in the higher projected picks than the lower ones. Is that a problem, or did you see a weaker ability to predict lower picks than the higher picks?
Yeah, I think I wouldn't really say that's a problem. I think that would just be kind of something that's kind of like natural in the draft, how generally there's going to be like a few top players who are going to be like very highly ranked, like say Shane Wright or Connor McDavid, who's usually a slam dunk #1 pick for the most part. Then as you get deeper down, there's going to be, it's kind of like a pyramid in a way. You're going to see like very high end players. Then as you get deeper down in the draft, there's going to be like a wider and wider range of players at each caliber is kind of how I would think of it. Like if you look at, say, models in the past that have tried to predict the value of each draft pick, you can see a very steep drop from the top pick to, say, like even the end of the first round. Then from the end of the first round to the end of the draft, it's pretty similar, like it's just slightly dropping off. So I guess like that's something in our model like that we kind of expect when we're doing a model like this for the draft, that there's going to be a wider range later on in the draft.
Yeah, no, and I think your example with comparing two different drafts with different depth, as you showed us in an example, really nicely show this example as well. So thanks a lot, really interesting work, and look forward to see what you're doing in the future. So with that,
thanks for having us.
Thank you.
So let's go to the next speaker or speakers. So here we have Cédric Ramqaj and Thibaud Chatel from NLA Ice Data in Switzerland. So please take it away.
Good day, everyone. My name is Thibaud Chatel, and I am with Cédric Ramqaj.
Hi, everyone.
So we are both from the Analyze Data project that is covering the Swiss National League. And we are very pleased to be here today to present our paper on score and venue adjustment on transition data in hockey. First, we would like to thank the organizers for this great conference and obviously for selecting our paper. So what are we talking here? At LNI's data, we are very lucky and unlucky sometimes to track our own data by hand. Which means for the past 3 years, we have tracked hundreds of games and tens of thousands of zone exit and zone entries. And I guess this paper is going to be a lot about quantifying some general feelings we have all had while watching a hockey games or tracking a hockey games for Cédric and I. And what I mean by that is that we all know the way teams are playing can change inside a game based on the score and the scenario of that game. And so in terms of transition, what we have seen very often with Cédric is that a team can play great in transition, you know, making some elite numbers on control exit, control entries for maybe 50 minutes. But for the last 10 minutes of the game, they're going to dump the puck more, you know, just to be safe because they are protecting a lead. And what it does is that at the end of the game, their transition data is going to be much more average than it should be just because of those last 10 minutes. And so the idea behind the paper was to quantify that assumption that the score of the game has a huge impact on how teams are transitioning their puck, you know, in terms of control versus not control and success percentage. And the second idea was also to check if the fact you're playing at home or on the road, you know, the venue adjustment also has an impact on transition. We have all heard about the play simple game on the road mantra, you know, where teams on the road are supposed to maybe play a bit safer, dump the puck a little bit more, take less risk, less control exits and entries. Did we see that in the data? That was the second idea. And really it joins what has been done on shots and goal metrics for the past 10 to 15 years. All those studies on score and venue adjustment, they have all shown that the score and the venue has a huge impact on who's supposed to attack more and who's supposed to defend more, you know, on shots and goals. But it has not been done on transition before this year. And as much as we would have loved to be the first to present something on transition, the king of stats, Blake McCurdy, published something earlier this year. The key difference, though, between his study and ours is that he used puck location from the NHL play-by-play as a proxy for puck movement between the three zones when we are actually tracking zone exits and entries. But what he found out is that, no surprise, if you're leading or trailing in the game, if you're playing at home or on the road, it has an impact on how easy it is to make zone exits and entries. You know, how fast you can do it or slower you are because you're facing more pressure or less pressure from the other team.
So, as Thibaud said before, in the last 3 seasons, so we tracked more than 400 games in the National League, and we used those transition events for these games and for this project. So we only use 5-on-5 data, and all the events were either classified as being either successful or failed. So for zone exits, we had 3 types of events. So carry and pass, which are both considered to be controlled exits, and dump exit, which are by definition uncontrolled. And for zone entries, we only had 2 types of events. So we had control entries and dump entries. Here we do not consider carry or pass entries. We only have control entries as an event. So in total, that represent 130,000 of events, and we split them between the different score states. So that would be either leading, tied, or trailing, and venues, so playing at home or on the road, and that for every type of events. So first, we wanted to have a look at some common knowledge that we may have on the game. And the first one being that leading teams will generally apply less pressure on the forecheck. So if we take a look at the chart on the right and compare how differently teams behave when they're trailing in a tie game onward than leading, so that would be the dark red bars, the gray bars, or the yellow bars in the chart on the right. So then indeed we can see that trailing teams, so watch the dark red bars, generally increase the rate of their control entries, carry or pass, as compared to a tight game or when they're leading. And second, a leading team will generally clear the puck more often, and indeed we can see that for both home and away teams, there's an average increase of more than 50% for both.
So if we look now at zone entries, the common knowledge again is that trading teams attack more, right? They're pushing to tie the game. And so here again, we see clearly that trading teams increase the volume of zone entries they're going to try. So we see for home team and away team, they move up from 5 to 10 more control entries attempt per 60 minutes, which is actually a 10 to 20% more attempts over the course of the game. So which is kind of a huge bump. The interesting fact is that trading teams also had a couple more dumps entries, but not that much, as we could have thought, because the common idea, I guess, would be that the defenses are playing tighter, to defend their blue line. And so the offensive team, the trading team, would have to try more dump entries, but that's not really the case here in the data that we see.
So now we take a look at zone exits again. So what about the share of exits attempted in control? So on average, there's a 10 points of percentage drop in terms of control exit attempted between trailing and leading teams. So at home, a trailing team will, for example, attempt 83% of its exits in control, while a leading team will try 73% of its exits in control. So it means that the leading team will use less carry or pass exits and increase the number of pucks dumped out of their zone. And for the away teams, as compared to team playing at home, there's a 2 points percentage difference, but the dynamics are basically the same here. So the score seems to drive the change of style more than playing at home or on the road. And the difference seems to mainly come from the number of pass of or dump exits. So one theory that we may have is that it maybe means that carry exits are more talent driven and less system dependent. Well, that could be an explanation. And another interesting finding here is that in terms of success rates, they seem to be less impacted by the score or venue than the style chosen to exit the zone.
So if we look at zone entries, are we going to see the same change in numbers? And I guess the one key idea here is that there is a double dynamic at play for zone entries when there was only one dimension that changed on zone exit, because on zone exit, the trading team is still trying to exit the zone. That's okay. And the one changing variable is to know if the leading team, the defending team, is going to forecheck less or not than before. But on zone entries, you still have that changing variable of the leading team, the defending team playing a tighter system in the neutral zone, playing tighter on their defensive blue line. But also the second new variable is to know if the offensive team, the trading team, is going to change its approach of entries to adjust to that tighter defense. And if you look at the share of control attempts, control attempts versus dump attempts, the first result that we see in the data is that there is no much difference at all. There is no much difference between home team and away team in terms of the share of control attempts, even at the tie game. And there is not much change between a training team and a leading team. Interesting fact is that away teams that are trailing are actually going to try more control attempts than when the game was tied. So the one assumption here is that the team playing style, the way the whole overall offensive mentality, the whole way they approach zone entries and the way they approach how to set up in the offensive zone matters more than the context of the game here in how they approach the entries. But the second part of the equation is that, okay, the teams are still trying to control as much than before, but they're supposed to have less success, right? Because the defenses are playing tighter and tighter. And again, the difference is not that huge in the data. So there is a small drop in terms of success percentage, but like for home team, it goes down from 77% success percentage when you're leading to 75% when you're trailing. That's just 2 points of percentage. And it's even less for away team. And for dump entries, the success percentage is also stable, but it even increases a little bit when you're trailing. And for that, the assumption is that maybe there is a balance between the defense that plays tighter, more alert maybe, but the offensive, the forwards also playing a more intense game because they're under pressure of tying the game. So at the end of the day, the two teams are playing a bit different, but the balance remains neutral at the end. We also know that defensive tend to let the forwards recover the dump just in order to pin them along the board and stop the puck from moving. But the actual, maybe very interesting findings that we came upon here was maybe the impact of the period you're playing in. And the question is actually, what if the big factor for zone entries was how fresh and organized the defense is? Because even the differences are, just small, not that huge, but we saw all over the board an impact of the second period of having the long change of playing far away from your benches in the way that attacking teams are trying more control attempts. They have better control success percentage and they have better dump success percentage. So that's something that maybe teams want to leverage in the future while playing in the second period.
So here, quickly, we have the formulas we use to calculate our adjustment coefficients, and it basically comes down to comparing the rate of any event to the rate of any event, but in a given context. So, for example, a home team in a tying game, for example. So, if we now take a closer look at the result of these different calculations, so we now have events that are not necessarily worse one as before anymore. So indeed, a play that is now less expected will now weigh more than before. And a good example of that would be a carry exit when your team is leading. So as we expect more dumps in that context, a carry exit for the home team will be now worth 1.08. And on the contrary, for example, a play that is more frequent or expected will have a lower value than one. And a good example of that would be a carry exit when you are trailing. It will now be worth 0.94 instead of 1. And for dumps, we just have to turn things around a bit more, as fewer dumps are always better. So dumping the puck out when you're trailing is less frequent. It means that it will now be worth 1.34. But if you're dumping the puck while leading, as it is more frequent, the adjustment is now only 0.84. So we can say that you've been partly forgiven for using dumps instead of controlled exits.
And so for entries, the big factor is in the adjustment is that you have an increased volume of entries tried when you're trading the game, and that becomes way more important than the small changes in the success percentage that we saw. So for a trading team, you're expected to try more control or dump entries, and so the value of both drops below 0. And on the other hand, a leading team is not expected to attack as much as before, and so any entry attempted is now worth above 1. Because you're not supposed to do that. So in conclusion, like we said in the introduction, this paper was a lot about quantifying some general things we all had before, and the historical assumption seems to mostly hold. A leading team control transition less because they are taking less risk, they dump the puck more. Trading team have an easier time exiting their zone, and they also attempt more zone entries. But the one thing we found is that home ice advantage is very small, especially compared to the score dynamics that are much stronger drivers on how teams are going to change the way they approach transitions. The unexpected finding, and maybe the most interesting one, is that the impact the second period seems to have, and maybe the aspect of the long change that is favoring the attacking teams over the defending team, with a more open game and more transition and more successful transition. So to end this presentation, I mean, in terms of future work, we would love to dig deeper into how teams especially approach transition in the last few minutes of the game, if they are trailing, like historically, depending on how much control attempts they have and what the success percentage was, which team successfully tied the game or not, and maybe what is the best recipe to tie the game in terms of approaching transition. We will also like for sure to look at the difference between the small ice in the NHL and in North America and the big ice in Europe, in terms of numbers. We tracked games at the recent Olympics played on the small ice by European players, and we clearly saw a drop in terms of control entries numbers, for example. It was way more difficult to make them on the small ice. And obviously, if we can find out other variables or aspects of the game that have an impact on the differences that we observe, we would love to dig into that. So thank you very much for listening, and we're going to take your question now.
Thank you very much. Very interesting presentation. So we have Cédric and Thibaud with us here. Welcome.
Hi, everyone.
Hi, everyone. Thanks for having us.
So I wanted to hear, I mean, this finding about the second period is very, very interesting indeed. So can you give some insight, or have you thought much about sort of advice to the teams, what this means for them? Should they change their strategy in the second period more than they already do? Because it's clear that they're already doing something, but is there something they can take advantage of there by the other team following that strategy?
Well, I think statistically is very small. First, it's more like an overall impression of something happening there. But for sure, we don't know if teams are doing it on purpose or if it's just a result of, having the long change, longer shifts, etc., etc. But knowing that, for sure, some teams could pressure, apply pressure on those control transition during that second period to make sure to take advantage on a more tired defense in front of them.
Yeah, and in general, just a quick comment or from you in terms of it. So we heard before Erik Wilderoth sort of talking about some of the same things, and here you've looked at a fairly big data set. Do you have some insights in terms of, because in some sense he had the risk reward, but he was grouping everything together. If you now do the same risk reward for home, etc., are there some additional layer of insights that can be provided from that?
Yeah, Erik's presentation was very.
Let's go, Thibaud.
Erik's presentation was very interesting. Actually, the Swiss numbers he showed was our numbers from a previous paper. I think there is a whole question around transition that can be studied on risk and reward and what you should do, what you should not do in certain contexts of the game. The score, the venue, where you are on the ice, the time, what time is it on the game for sure has an impact, and all of these are linked together in some ways. Cédric, you wanted to say something?
No, it's okay.
Yeah, no, very interesting work. Look forward to seeing more of your work, and impressive data set as well. So good stuff. So let's thank these speakers and move over to the last talk. So the last talk is going to be of David Radke at University of Waterloo, where he's a PhD student supervised by Tim Brecht. So please take it away.
What sets hockey apart from other sports is just how many different ways a player can pass the puck to their teammates. But how can this be mathematically captured, just like other stats have been for a century? In this work, we build a model to identify different types of passes in puck and player tracking data, and mathematically model different passing lanes available to a player. I'm David Radke, a PhD candidate in computer science at the University of Waterloo. This is work completed with my co-authors Tim Brecht and Daniel Radke, titled Identifying Completed Pass Types and Improving Passing Lane Models. The dataset we use in this work is the recently collected NHL puck and player tracking data. Tracking technology is located on each player and inside of the puck. Player locations are sampled 12 times per second and the puck 60 times per second. Locations are recorded in 3 dimensions with X, Y, and Z coordinates, and the origin is located at center ice. The tracking data comes with event labels, which signal the timestamp of an event such as a pass, shot, goal, and many more, and the identities of the players involved in the event. We previously published work in the AI for Sports Analytics workshop at IJCAI last summer, where we developed various metrics around passing and pressure from other players. In the paper I'm presenting today, we present a model to identify different types of passes and extend the passing lane model from that initial paper. We previously identified a passing lane as the available space between a passer P and receiver R, and identified that a passing lane should always assign a real numbered value, incorporate the area surrounding the passer and receiver, be asymmetric with respect to the pass direction to account for possible reaction times and sticks, and scale with respect to pass length. The size and shape of the passing lane is determined by a single parameter gamma. To show how the passing lane fits to the locations of players, consider this scenario with a passer, receiver, and 2 opponents. When gamma is 0, the lane is just the direct line between P and R. We grow the value of gamma until it reaches an opponent. In this case, the lane contacts opponent 1. The corresponding value of gamma is then the passing lane value. While a good initial model, there remains several limitations, such as only modeling direct passes and treating players as static objects. Our first contribution of this work is to identify different types of passes in the tracking data. The event dataset only contains labels for a pass and not what type of pass was made. We identify 4 different classes of passes. First, direct passes from P to R, rim passes where P rims the puck around the corner boards, and one-bank passes where the puck is banked off a straight section of boards. And a 4th class other, which includes various edge cases beyond the scope of this paper. Imperfections in puck locations or pass beginning and end timestamps make identifying each type of pass incredibly difficult. First, we identify direct passes as those which do not have any points within 2.5 feet of the boards. We chose 2.5 feet through observations, although we'd like to learn an acceptable threshold directly from data in future work. Since direct passes can also happen close to the boards, we also project the 5 possible ways for P to pass the puck to R, omitting corners and lanes through nets. If the pass with the least point-wise Euclidean distance error is the direct lane, the pass is also classified to be direct. Next, from the set of remaining passes, we classify rim passes as those with greater than 3 direction changes larger than 4 degrees close to the corner boards. We chose a threshold of 3 due to the one-bank passes described next and used the same 2.5 foot boards buffer as before. To classify one-bank passes, we leverage the unit circle from trigonometry. A one-bank pass, which typically bangs off the boards, will have 3 consecutive location points before and after the contact, such as PIA, PIB, and PIC, shown here on the left. The movement vector shown in red is moving at about 60 degrees located in quadrant 1 of the unit circle, which we show on the right. After contact, the movement vector would traverse the 90-degree threshold and then be located in quadrant 2. If 3 or fewer points are involved in a traversal over the quadrant thresholds of a unit circle, the pass is classified as a one-bank pass. In this example, these 3 points would be PIA, PIB, PIC, and the traverse threshold would be 90 degrees. Our next contribution is to extend the previous passing lane model to include one-bank passes, since it was only able to model direct passes previously. Our solution consists of modeling the one-bank pass as a direct pass through the theory of geometric reflections, ignoring things like spin or energy loss due to board contact, and then calculating the passing lane using all real and reflected opponents. To visualize this, consider this example in the neutral zone. The direct passing lane is modeled to be basically non-existent. However, P can make a one-bank pass to R, which is more open than this direct pass. To model this, we reflect the ice surface about the boards, including all potential receivers and opponents shown here. We can then approximately model the passing lane as a direct pass with regards to all real and imaginary opponents on the ice. For example, I'm unable to make this direct pass to my teammate. But if I consider indirect passing lanes, I can make a clean pass to my teammate with less risk of interception. Our second extension to the passing lane model includes the expected movement of all players. To do this, we utilize players' velocity at the time the pass is made and the expected duration of the pass based on machine learning from previous passes and various lengths. Now consider this example. The previous model would associate this scenario with a huge passing lane regardless of however these players were moving. However, P is likely to pass where R is going to be, instead of where they currently are when they're making the pass. So we project R to where they would likely be using their location, expected duration of this pass, and their current velocity. Opponents are also moving, but should only be projected until the puck passes their perpendicular location, since they can't really interfere with the pass after the puck has already passed them. Thus, we calculate the expected time for the puck to reach this dotted line and only project the opponents that far into the future. We then fit the passing lane using these projected locations instead of the player's actual locations. In this example, I pass to where my teammate is expected to be while also considering where the opponent will be, resulting in a completed pass and a goal. If I didn't account for the expected movement of all players, such as our previous model, I would have ended up with a very different result. From this angle, you can see how large the passing lane would be given our previous model. However, our new model considers this lane to be smaller, and attempting this pass results in disaster. We analyze our models on 198 NHL games from November of 2021. We leverage the tracking data and previously labeled pass events in the dataset. We find that 84.4% of passes in our dataset are classified to be direct. 10.2 are one bank, 2.6 are rims, and 2.8 are other. In our dataset, while forwards as a whole pass slightly more than defense, considering there are typically 3 forwards and 2 D, a defensive player on average completes 43% more passes than a forward. We parse the locations of one-bank passes by D and forwards, shown in the bottom figures. We find that D tend to make one-bank passes behind their own net and off their own half walls, while forwards typically make one-bank passes behind the offensive net and off the offensive half walls, likely back to the D. Since we can now model passing lanes for one-bank passes, we propose a new metric called the gamma ratio, which is the gamma for the direct passing lane over the gamma for the indirect passing lane for the pass that the player chose. Thus, if the gamma ratio is less than 1 for for a one bank pass, the indirect lane was bigger than the direct lane. Otherwise, the direct lane was actually bigger. We find that players chose to make the indirect pass when the one bank lane was bigger in 59% of one bank passes in our dataset. For an in-game example, consider this scenario. At time t on the left, player 86 has possession of the puck. Our previous model would consider number 28 to be the most open, the right defenseman. However, our new model suggests that the one bank pass back to number 3 is the most open. This ends up being the pass that 86 made and has a gamma ratio of 0.5. Completing this pass actually increases the passing lane to 86 from 0.3 to 0.98 in the right figure. This series of passes on the power play is called an up and over and is a common play with the man advantage.
This is what an up and over looks like in video. The indirect pass up the wall would circumvent the defender and open up the D-to-D pass. The rest of the clip shows typical power play movements and formations, ending with a goal.
Finally, we find that our model of expected movement reduces the error in receiver location in 94% of passes, and sometimes up to 5.2 feet. We would like to highlight various potential applications of our models at different levels of the game. For fans, our passing lane model could enhance broadcasts or augmented reality views to highlight the most open player or gamma value, as shown in this figure as an example. For coaching and reviewing video, our models could provide quantifiable impacts of positioning and movement for both offensive and defensive situations, and allow coaches to manually adjust the positions of players to study what their positioning could actually do to the available passing lanes. And for general managers, since watching every second of a potential prospect isn't feasible, our models could help quantify passing behavior in a game or across a season and provide insights into player skill or passing trends. We do acknowledge that our work still has several limitations. First, our dataset did not contain any data for incomplete passes. Therefore, our results may not be reflective of all passing behavior, and inaccuracies in the tracking data timestamps may impact our results. Future work hopes to involve gaining access to a dataset of incomplete passes and finding correlations between gamma values and pass completion probabilities. A natural extension of this work is to next model the passing lane for rim passes, and to include more advanced or realistic models of expected player movement, such as ghosting or physics-based models typically used in soccer. Finally, this work would not have been possible without our collaborators and people who helped out along the way in making this paper. Thank you.
Thanks a lot. Really interesting talk, really interesting work. Seemed to be a nice example of how we're sort of advancing sport analytics when we can take passing lanes into account. I want to welcome David, Daniel, and Tim. So great to have you here. And so I wanted to talk to you a little bit about sort of, I mean, you provided a little bit of applications for this. One thing that came to mind, and perhaps we discussed a little bit with Erik, was sort of this, not all situations are the same. And here you have a metric that sort of can capture the passing lanes. And in other words, how much pressure a player is under, for example, is there a passing lane, etc. Have you considered sort of future metrics that this type of passing lane work that you present here can enable?
Yeah, I mean, the whole idea behind the passing lane is to provide more context to decisions that players are making. And so I think future iterations could, tie in some more game context are they on the power play? Are they on the penalty kill? What you could parse by time of the game. You could parse by area on the ice. So yeah, I think future iterations just try and provide more context to player decisions, because obviously, you know, dumping the puck in on the power play is a lot different than dumping the puck in on the penalty kill, for example. So context is really the big factor in a lot of these analytics.
Thank you. So another consideration also, I mean, is the stick positioning. So we have a question in the chat that is asking, have you taken consideration to the stick location or the stick coordinates in your analysis?
Yeah. So I
I think
don't know.
Tim,
I don't know if Dan wants to go, but
well, I was going to say I think Tim mentioned it yesterday in his talk at the beginning, where that was one of the limitations that we see specifically from player and puck tracking data, because we don't necessarily know which way the player is facing, and so it's harder to determine the length of the stick. But it is something that we definitely like to incorporate going on in the future. I think this is the second iteration of the passing lane paper, so I think there'll be more to come in the future as we continue to get more data and look at it and come up with new ideas. But that's obviously a big part of passing lanes, because sticks, you know, a lane could be open based on where a player is standing. Sorry, a lane could be closed based on where a player is standing because their stick is in the right position, or it could be open because their stick's in the wrong position, that type of thing.
But the way I think of it is that the shape of the passing lane is kind of accounting for the reach of a player, and the parameters we've chosen seem to account for the reach of a player. So I kind of think of it as, well, we don't know where the stick is, but there is some kind of notion of there's a potential for a reach there that is kind of accounted for. I don't know if it's accounted for correctly, like if the parameters need to be a little bit bigger to allow for a really long reach, but I kind of think of it as it's kind of there without knowing where the stick is.
yeah, like what Tim said, the idea behind the motivation behind the shape of that passing lane that I showed in that talk, and even if you look at our previous paper and you look at that talk, we kind of discuss how the shaping asymmetric with respect to the direction of the pass tries to account for time, not only time, but also the opponent's stick. But, you know, Dan had a good point that passing lanes are a lot more than where the player's standing, because obviously you can pass under the stick, you can pass between a guy's legs. So it is something that we would eventually like to include in the model.
Nice. Yeah. No, but I definitely see sort of how the basic model you have is extendable to many of those cases. So it's really nice. Nice approach you're taking. One thing, I mean, now we have two active hockey players, I believe. Now I'm not accounting for you, Tim.
That's fair.
But yeah. Even though you're from Saskatchewan and probably could play up into these years.
Oh, I play, but not at the level of these guys. So.
Oh, okay, yeah. No. So I wanted to hear a little bit. So I mean, David, you're a defenseman. And one of the things that people are often evaluated there is, are you sort of a puck-moving defenseman that are quick to getting the puck up to the forwards? So can you reflect on how this type of metric or this type of things can be used to evaluate or identify good and bad puck movers?
Yeah, I mean, being a defenseman, I've had this conversation with Dan a lot. Dan's a forward, but you know, it's really a completely different game. And I mean, the past few days we've talked about the difference in the game between players and goalies. But if you think about forwards versus D, there's a bunch of different kinds of roles just within being a defenseman. You have defensive defensemen, you have two-way D, you have offensive defensemen. And I mean, most of the existing popular stats are very offensively weighted. And in the previous paper we had, it was at a workshop at Ichkai, which is a fairly popular AI conference. And we discussed that if you want to build a team using models of player performance and you want to kind of fill out these different roles, you need a more holistic view of what the player is doing. And so that was kind of the motivation behind those 12 metrics, but also behind tuning this passing lane model is like, you want a more holistic view of, is the player a good passer, or what kinds of passes are they making? What's their risk level? If anyone watched I don't know about people in Europe, it might've been too late, but if anyone watched the Tampa Bay New York game last night, there was a perfect example. I wanted to get it on tape, but the replay happened before I could end up recording it. But Steve Levy on the ESPN broadcast actually drew arrows on Kucherov's goal to go up 2-0. Actually drew arrows showing where players are headed, and then the Colorado defenseman the Tampa defenseman hit Kucherov right through the middle, and he basically pointed out players are moving away from this lane, and the defenseman saw that and ended up hitting Kucherov right down the middle. And I was sitting there watching the game thinking, this would be a perfect example. Maybe in a few days or weeks I'll end up pulling that game and I'll run the analysis, but I would love to, that would have been a perfect example of, here's this defenseman who had the opportunity to regroup the puck or kill time and maybe go D to D, but he ended up seeing an opportunity, and he had Nikita Kucherov at the far blue line, and decided and kind of analyzed the situation and was able to make that pass that eventually led to a goal. Obviously, in a lot of the metrics and analytics that have been presented this week, that would be a great assist, that, that's on the highlight reel and it's getting analyzed between periods like it was last night. But, maybe what if Kucherov loses the puck at the hash marks? The pass is still made, but that defenseman doesn't get any sort of, in these analytics that we've talked about this week, he might get some recognition, but it is one of those things where it's that was a great pass made at a great situation, and we can better capture that given types of passing lane models like this.
Yeah, no, thanks a lot. Really excellent work. Enjoying talking to you. So what I want to do now is I want to thank these speakers and all the other speakers that we've seen before. So great job, everybody. So with that, I want to close out this session.